All right, so we are now in the next section. So of chapter 4, at least we have a pretty decent understanding of vector spaces and subspaces. We now move to the topics of null spaces and column spaces, and I will do my best. Ready? So if we're interested in some ways that subspaces arise, well, subspaces arise in two different ways, right? So they arise when the set of all solutions to a system of homogeneous as the set of all solutions to a system of homogeneous linear equations. That's where we're going to begin just a second. And the set of all linear combinations of certain specified vectors. Now, let me start with, so the way I'm going to try to teach this is I'm going to work through an example of how to find null space. Then I'm going to go back to my Netflix analogy that I use for vector spaces and subspaces and see if I can bring in null space into that analogy. And then we'll continue with the study. Ready? So let me read the definition of a null space. So null space of, right? Null space of some matrix A, some m by n matrix A. First, notice the way they write it, null A. So that is the null space of matrix A. Well, what is that? What is null space of null A? What is a null space? Well, it's the set of all solutions of the homogeneous equation AX equals 0. Now, so AX equals 0, this is something you've seen before. It's just a homogeneous equation where you have a matrix A and you have a vector x, and when we multiply AX, we get the 0 vector. All right, let me see if I can start to make this come alive a little bit more, right? So let's start with the following system. All right, so we have the following system, and we're going to try to use that system to describe this AX equals 0 and describe what we mean by a null space. Okay? Well, let's go ahead and notice that looking at our system, all the variables are on the left side, and we do have 0 on the right side, so it's in this homogeneous form. And let's actually start with, well, what is A, right? In the equation AX equals 0, what would A? Well, A is just the coefficient matrix of that system, right? So I'm going to grab the coefficients of each of these variables. So that would be 1, -3, -2, -5, 9, 1. All right, so that is the coefficient matrix A. Now, what about X? Right, so we're AX equals 0. So in the context of this problem, first let me ask you, how many different variables do we have? Well, we have 3 variables, right? We have X sub 1, X sub 2, and X sub 3. So it's important to understand that the variables that we're dealing with this is a vector, right? These are all column vectors n by 1 vector matrices, but in this case we have 3. This is a 3 by 1. Now let's look at the right side of the equation, 0. So that is the 0 vector. So in the context of this problem, it would be 0. It would be it would still be a 3 by 1 column vector, but this is the way that the 0 vector would be written in the context of this problem. Now, let me read example 1. So example 1 says let A be the matrix, so I've already written it above, and we're going to come along and let U equal, so here's some vector U, equal 5, 3, negative 2. Okay. So what we want to do is we want to determine if U actually belongs to the null space of A. Okay. So as of right now, so does U belong to the null space of A? We can think about that for right now is if we did A multiplied by U, do we actually get the 0 vector? Right, because that would answer the question. But do you yet understand what a null space is? Well, maybe, maybe not. But it's basically, it's asking if vector U is one of the solutions to the equation, which is the same as asking if vector U is a solution to the system above here that I first wrote, which is the same as asking if the linear transformation of matrix A will map vector U to the 0 vector. Okay? This is kind of what you're seeing in this picture down below. I'm going to make this picture larger in just a second. But do you see how everything is mapping to the 0 vector? Right? So that's what we mean by what I meant by that linear transformation. But let's not get too far ahead of ourselves. The real question is, right? If I plug 5 and 3 and negative 2, if I plug them in for these variables in this initial system, do I get a true statement? Do I get 0 equals 0? So a much better way of doing this is just saying, okay, well, if I take matrix A, that coefficient matrix, and multiply it by this vector U, will I get 0? Because that will answer the question as to whether it is in the null space. All right, and well, let's go ahead and do that. So I would have matrix A, which is 1, negative 3, negative 2, negative 5, 9, 1. And I would want to multiply that by vector U, which is 5, 3, negative 2. Now, I'm not interested in going through the arithmetic here. That is, I've already taught you how to do this, but structurally, can we actually multiply these? Well, this is, remember, A is an M by N matrix, right? That would mean M rows, so this is a 2 by 3 matrix, to which we want to multiply a 3 by 1 column. Now, actually, I did mess up now that I think about this. When I wrote 0 in the context of this problem, I was thinking back prior to us doing these linear transformations. What I really should have waited, I should have waited to see what 0 would look like after we multiply. Because in the context of this problem, this is actually, the 0 vector should actually have 2 entries, right? And if we think about it, so let me get back to the structure. So we have 3 by our 3 in terms of our columns, and the rows here match, so structurally we can multiply, but this was the part that I got ahead of myself. The result is actually going to be a 2 by 1 matrix. So if you were to multiply these out, you would, which is not bad, you would end up getting 5 minus 9 plus 4, which is 0. And then you would get negative 25 plus 27 minus 2, which is also 0. So, yes, this is in the null space. Okay, so let me read a theorem to you. So, the null space of an m by n matrix A is a subspace of Rn. Okay, so let's pause for just a second. So, a subspace of Rn. Equivalently, the set of all solutions to a system Ax equals 0, where you have m homogeneous linear equations and n unknowns, is a subspace of Rn. So, all right. Let's go to the next page. Let's make sure we have a decent understanding of what just happened. So the way that you want to think about this is, let's take a look at the picture here in figure 1. And what you're noticing is the line, right? The line in figure 1 is a subspace of Rn. And what you're noticing is, notice how vectors are mapping to 0 in Rm. That is important because that means that we can make a statement that a null space is itself a vector space, right? So if it's a, remember we said in the previous video that all subspaces are themselves vector spaces. So that means that if the null space is a subspace, then we can also classify it as a vector space. But hopefully, if there's still a little bit of confusion, and I would assume, I would actually be highly impressed if there is not, then maybe when I get to my Netflix example, we can clarify a little bit of the confusion. So one more time, let me read this theorem because this is important. The null space of a matrix A is a subspace of Rn. That is the main takeaway here. It's just a linear transformation. You can have a back to the 0 vector. All right, so here is one more attempt to, I'm pushing this Netflix analogy as far as I can. So let's say every title that you can stream on Netflix, right? That means movies, TV shows, documentaries, all those are some vector v sub x, right? That would mean v sub 1 is a movie, v sub 2 is a movie, v sub 3 is a TV show, and so forth, etc., etc. Now, for our analogy, we have been thinking about the vector space as all the possible, or all the titles available that are on Netflix, right? If there's a movie that just hit the movie theaters, it's not yet on Netflix, so that's not in this set. It's not in the vector space. V is all the titles that you can, let's say, stream on Netflix right now. Now, the scalars that you attach to each vector, they represent the number of times you watched a single title, right? So if you had 4 v sub 1, right? If you had 4 v sub 1, that would mean that you watched whatever movie v sub 1 is 4 times. All right, now, what does the 0 vector mean in this analogy? So let's let the 0 vector, right? That's going to be the initial suggestions of titles that Netflix thinks that you would like. The initial suggestions when you first log in, right? That's, you just opened an account today. You have no viewing history. So this is the set of titles that are suggested to you by Netflix at first login. Now, a subspace, the way we've been thinking about a subspace of V, is these suggested titles that you would see if you logged into your Netflix account today, right? So because Netflix has been keeping track of your viewing history, they know how many times you watched V-Sub 1 movie and how many times you watched V-Sub 2, etc. So based on that linear combination, they are going to have a set of movies that are suggested to you based on your viewing history. All right. Now, let's see if I can push this. I don't know how far I can push it, but we'll see if we can push it, this analogy, into a null space. Okay? So let's let matrix A, right? Remember we have that AX equals 0. Remember this equation we've been dealing with. So let's let that A represent, so that's some M by N matrix. And we'll say that M, right, that would be the row. M is going to represent genres, so drama, action, etc. And we'll say N is going to represent each title that's, or just titles in alphabetical order, maybe. Again, if I assume I could have thought through this analogy more, but I think it's the majority of what I'm saying is safe. It's, again, if you push an analogy too far, it's going to fall apart, and if I'm too specific, there's no point using it, right? Because the goal is to try to help you understand what a null space is. The goal is not to try to find the null space of Netflix, okay? So that's not my goal. So now what we're going to do is we're going to so obviously the entries that would be in your matrix A, those entries are just going to denote the number of times a title in some genre was watched, okay? So in this case, how can we think of the null space of A? So you remember how there was that mapping to 0. So in other words, if you log into your Netflix right now, and you're seeing all the suggested movies that Netflix thinks you might like based on your viewing history. If we think about a way of undoing your watch history, right? If we think about the null space of A as representing the set of movies that, if watched, it would reset the suggested title page back to its default suggestions, right? So X is some set of vectors, some set of movies that you would have to watch, and some amount of times that you would have to watch them, such that when you do your A times X, you can reset your suggestions. Does that make sense? So you can think about the null space as a way of mapping back to the initial suggestions when you first logged in. Okay. Let's actually do another example. So, example 2, let me read. It says, let H be the set of all vectors in R4. Now I want to make sure we understand R4. So that would mean we have 4 variables, right? So R4, notice that since every point in R2 is some xy point, right? But in R4, we would have, our vectors would take on the following form: x1, x2, x3, x sub 4. Now, so H is a set of vectors in R4 whose coordinates A, B, C, D satisfy the following 2 equations. So, in our case, so for every vector in H is going to take on the form A, B, C, D, right? These are vectors in R4. These are going to be vectors in H. But it says that they must satisfy, in order to be in H, they must satisfy the 2 equations written, which was A, let me write them. So it's A minus 2b plus 5c is equal to d, and c minus a is equal to b. All right, so vectors in H take on the following form but must satisfy the following 2 equations. So how do we go about this problem? In fact, what is this problem asking of us? So it asks us to show that H is a subspace of R4. Now I'm going to do that, but I'm going to be using this this theorem that I've written at the bottom of the page. So how do we go about showing that H is a subspace of R4? Well, first thing you should do is you should start to view this as a system. Now, since we're dealing with homogeneous linear equations, the first thing I'm going to do is I'm going to set that system equal to 0. Ready? Let's do that. So if I set everything equal to 0, this would be A minus 2b plus 5c minus d equals 0. And I'm going to line it up letter under letter. So now this would be negative a. I got to bring the b to the left side, so this would be minus b plus c. There's no entry for d, equals 0. Okay, so let's go ahead and identify what is A. What is our coefficient matrix here? Ready? So we're going to grab all of the coefficients attached to these variables, as well as 0 for the placeholder there. So this would be, matrix A would be 1, negative 1, negative 2, negative 1, 5, 1, negative 1, 0. All right. So what I'm going to do right now is I'm going to set up AX equals 0. And then I'm going to go back to this theorem. Ready? So AX equals 0. So this is going to be, I'm going to rewrite matrix A. Now, that's going to be multiplied by vector x. Now remember, all the vectors in H take on the form A, B, C, D. Now that's got to be equal to the 0 vector. So let's go ahead and identify so start with matrix A. This is a 2 by 4. And this is a 4 by 1. So the form of 0 is going to be a 2 by 1. So this is a 0, 0. Now, to answer the question, I'm going to have to go back to this theorem here. Ready? So the null space of an m by n matrix is a subspace of Rn. That sentence is where we want to begin. So we wanted to show that H is a subspace of R4. Okay? So let's identify, in this case, based on, I want you to look at A. Let me, right below that. I want you to look at A, matrix A, which is an M by N. I want you to tell me what is M and what is N. Well, if you're looking up here, so you're looking at here, so M was 2. What does that mean? That means 2 homogeneous equations, right? Rows, 2 rows, 2 homogeneous equations. N was 4. That means 4 unknowns. So in this case, all that we're doing is calling on theorem 4 to show that your null space of an m by n matrix is a subspace of Rn, but in this case, n is equal to 4. So clearly, if your null of A is always of Rn, it's a subspace of Rn, then in this case, if n is equal to 4, then that is the way we show that it's a subspace of R4. All right, we will pick up again in part B. I will see you there.